This is another example that I did in class, but I want to do it a little more cleanly here. What you see is a model for a physical wire connecting a power supply V1 to a load circuit, which is modeled by a changing current source. The load begins as 1 milliamp and becomes, when the switch closes, becomes suddenly 10 milliamps. The resistance and the inductance and capacitance are all models for a physical wire. So physical wires are copper. They have some resistivity. They also have some inductance, and any conductor has some parasitic capacitance coupling to the environment. So when we look at this sort of problem, we might initially wonder if we can use series or parallel approaches, because this looks, at least at first glance, not to be an either series or parallel circuit. But we can write down familiar sorts of equations. First off, let's note that after t equals 0, when that switch closes, this becomes really just a single 10 milliamp source. So this load current is fixed at 10 milliamps from time t0 onward. I don't really know where to start this, at least I wouldn't if I was sitting taking a test, so I'm going to write Kirchhoff's current law here at this node. And what I'll get is that the source current, or the load current, plus the capacitor current, so the current going down this way, we'll call it IC, and the current going this way, we'll call that IS because that's a source. And this current over here, let's call that IL, that those things add up together as follows. IS plus IC is equal to IL. I can also write a voltage loop around the left-hand side. And when I do that, I'll see first that we hit V1, but we hit it the wrong direction. It's a voltage rise, not a voltage drop. So let's get minus V1 plus IL times R. That's the voltage across that resistor. The voltage across the inductor is L DIL dt. And then the voltage drop across the capacitor, let's say that's what I'm going to solve for. So I'll leave that as Vc. If this all is equal to 0, which is true of any loop, then what could we do to solve directly for the voltage? In class, I showed, roughly speaking, how to fiddle your way through to solve for current, but how could we solve directly for the voltage? Well, the key is to take this substitution here and put it into those two spots. If we do that, we will get as follows. We'll get minus V1 plus IS. And what is IC? Let's also go ahead and say that that is C dV dt, because what I'm trying to do is I'm trying to get rid of any and all occurrences of current. So C dV dt, where this is Vc now, that all is times R. And then with L di dt and this substitution, we'll get that to just be L times C d squared v dt squared. And then we still have our Vc term that we're going to try to solve for, and then that whole thing is equal to 0. If you choose to use the same conventions we've been doing in the class, which is to say that we want no coefficient on the second derivative term, and you move V1 to the other side, and since IS doesn't depend on dVc, we can move it to the other side as well, you'll wind up with the following second order differential equation. D squared v dt squared plus R over L dv dt plus 1 over LC Vc is equal to V1 minus IS times R. And this looks a whole lot like the series equation that we found. In fact, the only difference really is the inclusion of this ISR term. Hopefully you can see that if you were to write down a characteristic equation, make the assumption this is A e to the st or something like that, that this would obviously have the same sorts of behavior as the series circuits that we've worked with before. The main difference is that the voltage is decreased slightly by whatever load current you add. Any final values and initial values will also be affected by those currents. But at the end of the day, the underdamped, overdamped behavior, etc., is all dictated by the same sets of equations as for the old series circuit we've been working with.